All right, so what I've done is I've taken the example we just worked on, that natural log of x squared plus y squared, and I've plotted the surface in this CalPlot 3D. I know a lot of y'all prefer GeoGebra, and it's a lot nicer to look at, but the vectors are harder to draw on that one, so that's why I'm using this. But so this is the surface natural log x squared plus y squared. Here's our x direction and y direction right here. We cared about the point 1 minus 3. So what I'm actually going to do is change our view real quick to kind of go 0 to 4 and minus 4 to 0. That way we're just looking at that specific portion of the graph that contains the point 1 minus 3. And I'm going to show us the contours real quick. So here are slices of different heights, z, of the f of xy. Here's the -1 slice, the 1 slice, the 2 slice, so on and so forth. And then we always draw those little slices as the level curves in the xy plane. So here they are down there in the xy plane, those same slices we took of the surface just projected down in the xy plane. And wow, rotating this surface is very difficult. Oh gosh. All right, this is just going to be our view of it now, I guess. That's fine. And we're thinking about the point 1 for x and -3 for y. So that's right there on the surface. That little dot that was just created tells us the point 1, 3. And then I already wrote up some things that will show us the components we cared about for this problem. So we wanted to find the derivative of the surface. We've got the surface at this point in the direction 2 minus 3. So this vector right here is the vector 2 minus 3, super long. We needed to find the unit vector in that direction. So that was our first step in solving the problem. And then what we did was we calculated our gradient vector, 1/5 minus 3/5. And it's, oh, I should use a different color. I'll use blue for the direction we're going because it matches the point, and then black for the gradient vector because it's going to match the level curves when we get to that point. But our directional derivative was supposed to tell us the size of the derivative represented by the gradient in the direction we wanted to go. And so kind of you can imagine that, here, this is the best way to look at it in this direction. So we want to follow this vector along the surface. And when we follow that direction along the surface, we go up the curvy part of the surface. So z increases. And that's why we had a positive number for the directional derivative. And these two vectors run in a pretty similar direction. So we held on to a lot of the derivative change for the direction u we were going. Real quick, what I want to do is somehow get a view back to this that lets me look at it flat up and down. Okay, that's about as good as I can get it. And I'm going to hide the direction we were going real quick to just kind of touch back on this thing that we said was true about gradient vectors earlier. So this is still my gradient vector that we calculated. Here are the level curves. And you can see that it's pointing from the level curve for this part of the surface to this higher level curve for the increased value of the surface. And it really is perpendicular to that level curve. I just thought it would be good for you to see it come from a computer and not just from me, because my pictures aren't always the best.